How many people were here this morning to see this morning's talks? Almost everyone. Okay, this one will be different. Today, this afternoon, I'd like to talk a little bit about the experience of flying on a space shuttle mission to help construct the International Space Station. As an example, I'll use mission number 130. It was just about 2 years ago, and we'll talk about what we did. It was the last major construction mission to the International Space Station, which, by the way, is up there today with 6 crew members on board. And the crew of the Space Shuttle Endeavour that flew up for this particular mission I'm going to talk about, STS-130, is shown here. Most shuttle missions have 7 people on it. We only had 6. It seems kind of strange to be talking about the shuttle now that it's gone, but this was only 2 years ago. We only had 6 because we were carrying so much equipment up to the space station that we actually needed to reduce the crew by 1. Talk a little bit about training. We don't fly in space very often, and so in between flying in space, we each have technical jobs, and we train to do our astronaut job. We're constantly learning to do new things. But one thing we have to do is maintain our skills to integrate lots of different information coming at you very rapidly, communicate that information with your crew members and with other people who are back home to come up with a solution, sometimes very quickly, in an environment that could be very dangerous. So the way we do that when we're not flying in space is we fly jet aircraft. And so this is a NASA astronaut T-38 that we use to fly, and we have several of these that we all fly. Lots of safety equipment involved with helmets, oxygen masks, parachute straps for the ejection seat. You've got a flight suit and gloves that are flame-proof, so you can't burn yourself. It's all about safety. Our job is constantly about safety because it's in a dangerous environment in space, and things happen that we didn't expect all the time, almost every day. So I skipped the whole year and a half, almost year and a half that we trained for this mission for. It was a very complex mission, so we had a lot to learn, which was part of the fun. And so finally it was time for launch day, which was the middle of the night. And we climbed on board the bus, climbed onto the shuttle, and launched into the night. And here are some numbers about the space shuttle. It's a little bit hard to believe. The whole space shuttle with the orbiter and the fuel tanks and the 2 big rocket engines weigh about 4.5 million pounds. Only 4% of it is the empty shuttle itself. So it's almost all propulsion system. The landing weight of the shuttle itself is about 250,000 pounds. The main engine weight and the thruster there, that thrust to weight ratio is tremendous. That's a thrust divided by weight of about 70. The total engine thrust is over 7 million pounds. And so on liftoff, you have more than, you have about 3 million pounds excess thrust is what you call it. In other words, more thrust than you weigh. Your fuel burn is absolutely huge, but out of all that fuel, you get tremendous performance too. Your initial climb rate, I've got this in feet, but if you're a pilot, the rate at which you can climb through the atmosphere is always important. This is 42,000 feet per minute, which no other aircraft has anything like that. And the sink rate when you come back down is about half that. Also an impressive number. So in this day and age of thinking about the environment and trying to use as little energy as possible to get the job done, we look at the gas mileage. It's very bad. It's about 2 meters per gallon of fuel. But then you coast for about 2 weeks without using fuel. So it comes down to about, in American terms, about 8 miles per gallon, which is pretty good for a large truck. I showed this morning, the launch performance, how quickly you get up to speed. But there's something here I didn't point out. Look at the 4-minute mark. Here's the altitude in feet, 320,000 feet. And you've climbed very, very rapidly. 4 more minutes later, 8.5 minutes, about when you're entering your first orbit, you're not much higher at all. Why is that? It's because the initial part of launching into space, the job is to get out of the atmosphere. So you go almost straight up. That's because you don't want to go through the atmosphere too fast to avoid aerodynamic heating. But once you're up and out of the atmosphere, you've gone through it perpendicularly, then you bend over and you start going fast. And you actually come back down a little bit, use a little bit of gravity. So the second half of your ascent, you're actually not going up, you're going that way. So you can go very fast. How many people have seen what it looks like inside a space shuttle during the launch? Anybody who's looked at YouTube probably, but this is this particular mission. It shows, I'll just give you a little bit of an idea of what launch looks like and I hope sounds like. What you're going to hear is a great big loud voice that is mission control, and so they'll be talking to us a little bit, and the rest of the voices you hear are the crew. And you hear the kind of interaction that we have. I won't try to explain everything that we're saying here, but you'll hear bits and pieces. The camera is mounted basically on the front, on the inside, looking backwards. So to this side is the commander, whom you can't see, George Zamka. Here we have the pilot, Terry Verse. Over there is the mission specialist number 2, Kay Heyer. And this is the flight engineer, me. Let's see if this works. There should be sound. But there's not. That's all right. It's mostly visual. You tell me when the engines start. It's not very long from now. Remember, the engines start for a while you're on the ground, and then you leave the ground. Oh, I wish we had sound. Now we leave the ground. Oh, it stopped right there. Huh. It's plugged in, I swear. Impedance mismatch. Okay, we just went through a cloud layer. Looks like the computer's stalling a little bit here, but it gives you the idea. The initial launch is quite violent, but not too long afterwards it smooths out pretty well. And it's not so interesting if you can't hear the sound, so I'm sorry that this system isn't working for us today, but we'll move along. It was a nighttime launch. It launched about 4 in the morning and looked pretty good from the ground as from what we hear. The first thing that we do once we get into orbit is drop off the fuel tank, and we power away from the fuel tank, but the fuel tank falls back into the atmosphere and then disintegrates. And we want to make sure it does that, so we open a valve to vent the remaining pressure. And you can actually see that happening. That makes the fuel tank tumble and falls more rapidly into the atmosphere. Okay, there we are. Who took that picture? The International Space Station. And it shows our payload, which was a piece of the space station. This has the poetic name of Node 3. But it also has this cupola of windows, which starts out there, and then we move it over here, and you'll see that. But that's what we went up to deliver. Here's our target, the International Space Station, glowing brightly in the sun. After 3 days in space, to come across this thing in space, it actually, I don't know why we call it beautiful, but it really does look beautiful when it's the only human-made thing up there. You can see a couple interesting things on the space shuttle here. You can see the black tiles are where we expect the heat to be the worst when we come back down. Through this hole here is a instrument that tracks the stars, so that without any other instrumentation on board, we can actually figure out what is the attitude, the orientation of the spacecraft in the sky. So we have one here and one here. So they look that way and we can find our orientation. If you're here this morning, you know we flip over and show our belly to the International Space Station so they can take pictures. This time there was nothing sticking out, so we didn't have to go out and fix it. Got an impressive view from the rear. Notice all the different sizes of rocket engines. These are called the main engines for obvious reasons, and they only get used for the first 8 minutes. After that, you don't use them anymore because you don't have any fuel. However, these guys do two very important things. When you're going up into space, you don't start with a circular orbit. You start with a very elliptical orbit because you've just come from the Earth. So you're not really going in a circle around the Earth at all. If you left it that way, you would come back into the atmosphere on the other side of the Earth about 45 minutes later. So what you do instead is you do another, what we call a burn. You fire rocket engines to give you more thrust just when you need it to make the orbit circular, and that's what these two engines do. They are also the engines that bring you back home. So when it's time to come home, you turn and point these into the velocity vector, so you're flying backwards. You fire these engines for a few minutes, a couple of minutes, and it slows you down enough to drop your apogee, or your perigee actually, into the atmosphere. And then you use aerodynamic braking. You put belly first and you slow down, and that's how you come back down. And then these tiny ones, and there's smaller ones yet, these are used to change the attitude of the spacecraft while you're in orbit. And the shuttle is actually capable of holding an inertial attitude, in other words, an attitude relative to the universe, of 0.03 degrees, which is pretty amazing for 1970s technology. There's the crew, happy to be in space. Okay, here's our payload. First thing to do is to put it on the space station. So we reach out with we have two robot arms, one on the shuttle and one on the space station. We use the space station one here, reached right into the payload bay of the shuttle, the open part in the back, and pulled it out while we had two guys out spacewalking. And the reason is they had to prepare the payload before we took it out and also help hook it up once we got it in place. So a very complicated sort of dance between the folks who are doing spacewalks and the folks who are doing robotic operations here. Lots of people at work. I missed one, didn't I? I always want computers to go faster than they want to go. When you build a new room on a building, it has to have all kinds of things. It needs power and cooling and air conditioning and nowadays data. If you're going to use it as a scientific laboratory, it needs more things than that too. So all of those things need to be hooked up. The philosophy of building the space station has been the mechanical linkages between the modules is done sort of automatically with remotely controlled latches and motors that drive them. Everything else is done by hand. So if you want to hook up all the cables and wires on the outside, you have to go outside and do that. And if you want to hook up all the cables and wires on the inside, and including some of the fans and air conditioning and things like that, mechanical items, you have to do that too. So we had a team for each. We had a team to go outside and to hook up the cooling system. Now, why do we need cooling in space? What's the big deal about cooling in space? Student question. What's so different about being in space? We have big solar arrays and they collect electricity, right? So what do you do with all that electricity? You run stuff. You run things that have fans. And what happens to that electricity after you drive it through an electronic component or motor? It turns into heat. What happens to heat in space? What it doesn't do is it doesn't go up because there's no up. So many things you have on the ground, all you need is little vents, and you will get natural convective-driven cooling because the heat going up needs to be replaced by cooler air coming in from the sides or somewhere else. It doesn't happen in space. So we have to actively take that heat away. The way we do that usually is with a water system, and then that water system, how do we get rid of that heat? We go to a heat exchanger. Can we take the water outside in a pipe? No, why? Freeze right away, right? So we need some other kind of fluid that's not going to freeze at space temperatures. So then we need a heat exchanger between the water and that other fluid. That other fluid turns out to be ammonia. But you can't have ammonia on the inside, because if we had a leak, you do not want to breathe ammonia. It will kill you right away. So now we have a toxic system on the outside, a human-friendly system on the inside, and so this is our cooling system. So if you bring up a new room for the facility and put it on, you have to put this cooling system, this ammonia cooling system, on the outside. And so that's what our spacewalkers did. Now this is I show this picture because it's horribly complicated. And this is what you have to learn to recognize absolutely everything in this picture. And there's some very important things, such as an ammonia cooling line, electrical power cables, a data cable, and oh look, there's a spacewalker. Oh no, look, there's another one. Okay, inside we had another team whose job was to wear really ugly shirts and do all the wiring on the inside of the node that I explained before. So we spent several days, actually more than a week, doing all of these things. It's a lot of fun. It was a brand new thing, and not everything fit. Not everything worked correctly. So we have to get out our tools and start improvising and making things up. And it helps to have had a neighbor like Paul, who's an experienced airplane mechanic, to teach me a few tricks on how to do such things. Having a tool in your hand is always one of the happiest things you can do, especially if you're floating. Wearing Velcro all over your pants is a very important thing to do too when you're in space. Trying to figure out what this is. Oh yeah, okay. So this is my book of brains. This is just a notebook that I made. It keeps all my little notes that I don't think I can remember well, but just like the notes that you make for your exams. Once you make the notes, then you know it. So you never really open it. There's Kay putting out in an entire panel in the node. I know this isn't too fascinating to you, but imagine having this job in space. It's a lot of fun. Looking for tools is hard. Losing a tool is really bad. I lost a little socket. I had to make a lot of apologies for that. It's still up there. This is the cupola. It doesn't look like much. This is the most interesting part of the whole space station if you're a human being, because it has windows in it. I'll show you. So we took it off the part of the node where we launched it and put it on the part that looks down towards the Earth. Here's our guys, Bob Benkin on the right, Nick Patrick on the left, getting ready to do spacewalks. I didn't do the spacewalks this time. As kind of the senior guy on board, my job was to be the coordinator of the spacewalks from inside. There's those lucky guys out there working on it. You can see a couple of interesting things. This is the sun visor to keep your eyes shielded when the sun is so bright. Your gloves have heaters in it, and here's a little turn-on switch for that. Here's a camera. Here is a nitrogen-powered jetpack in case your tether breaks and you go floating off into space. And these little holes are nitrogen thrusters all over it. And if that happens to you, you reach back, pull a little handle, and a hand controller comes out. It's actually right under the camera. And then you fly it almost like a little aircraft to get yourself back to the space station. It's pretty neat. Every spacewalker has that. Great view of the whole environment there, showing Russian Progress and Soyuz. These lights here are how you continue working. You're outside for about 7 hours at a time. So the sun comes up and down. You go around the Earth every hour and a half. So you get a sunrise and a sunset every 45 minutes. So you need your lights about half the time. There are times when you're doing a spacewalk when if you look down, you sort of have to convince yourself it's okay, you're not going to fall. Well, we were working very hard on the inside. These guys were working very hard on the outside. And at one point, we had a view through one of the windows in the new node of Bob Benkin enjoying himself out there. So here's what that window view looks like from the inside. 7 windows. You can kind of float right up into it here and look out You can see a view of the shuttle. You can see the robot arms. It's a tremendous view. And whether you're looking up through it or looking down through it sort of depends on how you think about it. It's constantly changing view depending on whether it's day or night. It's a good place to take pictures of the crew, although mostly when you went there, I mean, we put it on for the first time, so everyone was fascinated with it, so you couldn't stay away. And so mostly it looked like this. Its purpose, the reason this is there is so that when we're doing robotic operations, so we've got a great big robot arm, and other vehicles come up close to the space station, and they don't dock. We reach out, some of them do, but some of them don't. We reach out and we grab it with the robot arm, and then we make it dock that way. And so this provides a crew an immediate three-dimensional view of it. There's some secrets I can't tell. These are the Russian spacecraft that we all know and love very well too. The Soyuz and the Progress, that's the cargo vehicle. This is the one where the humans go, but obviously they're based on the same design. Great view of the shuttle Endeavour in this case. Looking a little well used because I think this was its 27th mission. So after spending about 10 days on the International Space Station and adding this thing here, and here's that cupola with the windows looking down towards the Earth. So this is all the new part. We pulled away, and remember when we came up to the space station, we turned around and they did an inspection of us. When we left, we fly around them and do an inspection of them. And why do they need an inspection? Because they're in the environment of space. And there's about 3 different things that happen to materials in space. One is the thermal cycle is quite high. You get hot, you get cold. And this happens twice an orbit. So it's going back and forth and back. So this is a thermal fatigue that affects everything to some degree. Another is that you're actually not very far out of the atmosphere. And there is atomic oxygen. Think about the chemical implications of atomic oxygen, not bound with anything. It will bind with just about anything. It loves everything. And so that forms a way that things can actually get corroded in space. And it affects some of the softer materials, sometimes to the point where they need to be replaced. And finally, you have the space debris that's coming from all over the universe, sometimes just in our own orbit. A lot of it is human-made, which can form holes and craters on the space station. And if they're small enough, we might not know about it. So that's the purpose of the inspection. So we flew around it. We cast our own shadow on the, on the solar arrays, for which we had to apologize. Really a beautiful view to think that there's humans living aboard that. Hey, here's something you might not know. Remember I was talking about getting rid of heat in space? Okay, here's another thing that a lot of people, engineering students might know this, but in general, people in the world think, these must be solar arrays. What are those? Those are the ammonia radiators. Those are the ammonia radios. So that's how that whole process of heat rejection, that's where it finally ends up. These solar arrays track the sun this way, like a big paddle, and then they twist also. Lots of nice pictures. You can see the whole string of the Russian side of the space station. I talked about our inspection boom. That's a good picture of it. This one has no joints. It's just one big, strong, straight piece of pipe that our sensors are attached to the end. And that we use mostly to reach underneath the spacecraft. There we go. There goes Endeavour, leaving the International Space Station and flying off into the sunset. and still wearing ugly shirts. Optics experiments are always fun. Anybody ever been to the Massachusetts Institute of Technology, MIT? Yeah. We had 2 people on board who have a history there. This will give you nightmares. This probably would too if you could hear me playing this, but this is one of the things I love to do is play music, and the privilege of playing music inside the cupola on the International Space Station was certainly the best musical experience I've ever gotten to have. Let's see if this works. All right, this is a physics experiment demonstrated by a human being. Try this at home. Did you think that was possible? I didn't. This is what you learn at MIT. The principle of conservation of momentum, angular momentum. I'll finish this up with just a few photographs of the Earth. The Earth is constantly changing, and your position above it is constantly changing at the rate that you're going. You know, I could tell you where these places are, but I don't want it to matter where the places are. The point is that it's a beautiful Earth, and it's worth protecting, and it's worth exploring, and it's worth flying above, going away from it, and coming back. As my friend Dave Brown once said on his first and only space flight, he looked back at the Earth and saw some of these scenes. He said, if I had been born on some other world, I would want to visit that place more than I would ever want to go to space. Actually, that Mount Everest is in that picture. Yep. If you're interested in meteorology or fluid dynamics or Earth resources, or almost any kind of science, being in space is a great place to ask more questions, to make you more curious. Convection thunderstorm buildups in the middle of a dust storm over the Sahara. I never knew that happened. This, to me, is the most amazing thing about being in orbit around the Earth. The Earth is really huge. The atmosphere is really small. Now, I've spent my life as a pilot, and I always thought that the Earth, that the sky was infinite. And flying in the sky was just, you can just go up and up and up. That's just not true. Look at you can just barely see the curvature of the Earth. So think about the radius of the Earth. There's your atmosphere. That's it. It's like a thin wrapping. So when people say that the atmosphere is fragile, it's true. A lot of cloud pictures because I'm interested in meteorology. I'd love to talk about why those patterns are in the clouds. Lucky for you, we don't have time, but I would love to tell you all about that. If I were your professor and you were my student, I would say, what determines there's sort of an average distance between these convection cells? What determines that length scale? It would lead you down to the surface and under the surface of the ocean, the answer. But you could also ask, well, what determines the distance between sand dunes? Why aren't they this far apart? Or why aren't they this far apart? In some places of the world, they're different. And that would lead you to answers that would have to do with the speed of the wind and the size of the sand and the density of the material that makes the sand. You get a sense of depth sometimes when the shadows are cast by the clouds on to the rest of the surface. You can see ocean currents interacting with other, and sometimes in here, I guess not in this picture, you can see individual ships, which is pretty amazing. All right, we spent 2 weeks in orbit. We came back home as we left in the middle of the night. And our commander, Zamka, on the left and pilot Wirtz on the right did a good job. We landed right on the middle there. And there's the good ship Endeavour with its lucky crew to the right. And we're all, if you look, we're all kind of leaning on each other. We're trying not to make that show. But I know, particularly, I'm kind of holding the pilot up. It's his first time in space. It was my fourth. And he was about to fall down. And you don't really want to fall down in front of the national TV. So I was kind of holding him up there a little bit. And there was our patch come true. Our mission design was taken, obviously, right from that window that we installed. And then we made it come true. So that's an example of the utilization of the space shuttle from an astronaut's point of view. Any questions? Thank you. Thank you very much. Any questions? Go ahead.
Yeah, I have one question. It's very nice.
That's all right. I'll repeat the question. Although,
Vale.
yeah, there's been a...
¿Se oye, no?
Yep.
Yeah. My question is regarding, it's very nice working for building International Space Station, working in international environment with people from all around the world. But the question is, why don't you use, in the end, I mean, we are in the 21st century, the international system for units?
Oh, isn't that terrible? I have no good answer.
I have
for
read
that.
miles per gallon. I have been reading some figures about miles,
Yep.
inches, blah, blah, blah. But
Right.
what about...
The American culture has not embraced that yet. If you go just north to Canada, it's all metric, as it should be. But for some reason, the American culture has been very resistant to changing that. Some parts of engineering in the United States you'll find all metric, and other parts you won't. And the decision was made, against a lot of our wishes, early on in the space station development, that we would use what are called English units. So this is what we see here. So this is what we use. And in university, we teach the metric system. But here in old-fashioned NASA, sometimes we use the English. Go ahead.
You said you had, you do a lot of manual control when you're working on the spacecraft and the International Space Station. But what percentage of control during flight do you actually have, or is a lot of it now computer controlled? I'm curious how much of the team is actually making the maneuvers versus a computer.
I have the best answer possible for you in the name of Paul Dye, who's going to spend the next hour telling you exactly the answer to that question. So I'm going to wiggle out of that one. Thanks. That's a great question, and it's a question that has a lot of consideration for the future when we go further and further from the Earth, and you consider signal lag time, signal travel time. And it really becomes a much more interesting problem. What else? Anything more? Okay, thanks a lot. We'll reconfigure computers over the next minute, and then we'll have Paul Dye come back and answer your question.